So in this video, we'll talk about another test for whether the infinite series is convergent or divergent. And let's look at the current page here. We talk about the limit version of the comparison test, and please look at the criterion to apply this test. We require that you have to compare two infinite series, and all the terms inside both infinite series must be positive. And this condition is quite similar to the integral test we looked at in the previous video, right? And it means that if you see some negative terms, it may not be appropriate to apply the comparison test. And let's look at how you can proceed from there. We just compare the terms when n is big. And you see, when n is going to infinity, if we obtain that, the two terms are actually very close to each other. They may not be the same, but we will require them to be very close. In that case, the behavior of the two series we compare, they have the same behavior. If one of them is convergent, the other one is also convergent, right? And let's look at some examples now. So please look at the current example. My advice to do all this kind of infinite series problem is to trace back all the methods you learned from the easiest method on geometric series up to the current method. Let's check all the methods you learned, right? And for example, I don't think it is a geometric series. You can check it yourself. It's actually easy. There's no fixed ratio between the consecutive terms here. And if you use the M-term test, it's actually not working. So I suggest that you can check it yourself. If you take the limit, it is actually 0, and 0 means no conclusion for the problem. So it can be convergent, it can be divergent, we never know. And let's look at the later test we have learned, the p-test. Of course, it is not a p-series. It is not a p-series, so there's no chance to use the p-series test. And for the integral test, you may be wondering whether we can do it or not, because you see all terms are positive, right? So we satisfy the first condition. But you see, the point is, if you try to do an integral test here, it means you're actually integrating a very big fractions. You are integrating something like that, which makes sense. It makes no sense to us because this integration is just complicated. It's not impossible, but we try to drop something when it just takes too much time for us. So let's drop this integral test just because computationally it is complicated. And let's perform the current test, which is the comparison test now. The fact is you have to see what's happening when n goes to infinity. So let me write down the terms here. Let's look at these together. I think when n is so big, when n keeps going to infinity, the fact is as a rational functions, only the highest power term dominates the whole function, which means that when n is so big, the smaller terms don't matter to us anymore. We only need to write the highest power term like this for top and bottom, and of course n squared is cancelled as a common factor from the top and the bottom, right? And at the bottom you're left with only one copy of n. And by the comparison test, we have to check what happens to this infinite series of 7 over 8 times n. You see, we can pull out the common factor for the uh, 7 over 8 in front of the summation of 1 over n. And we have seen this for so many times. It is a harmonic series by the p-test, because now the p-series test means the p is 1 for an integral like this. So it means that, of course, it is a divergent case when the p is 1 by a p-series test. And by the comparison test, we can write down our answer here, because we understand that for the simplified fraction in the right-hand side, the infinite series for these terms is actually divergent. So the original series, we also know that it is divergent. So it's a result by the use of the comparison test. And the comparison test can be so useful if you're skillful in determining whether some complicated infinite series is approximately the same as another infinite series with some simplified terms. And let's look at other examples. So please look at the current problem. Can you try to determine what's happening to the term inside the infinite series when n goes to infinity? So let me write it down here first. You see, when n goes to infinity, these two terms are infinitely big because you are taking a 4 to the power, and the power is so big. When 3 as the base, you are taking the power to to a power n when n goes to infinity, both these terms are so big, which means they determine the whole fraction basically because they are the dominating terms and 3 as a constant is so small. So it means numerically speaking, when n goes to infinity, we expect that our current fraction is numerically very close to this one. And by the comparison test, we only have to look at the infinite series where the terms are 3 to the power n divided by 4 to the power n. And I think this one we can determine it because this one is basically the same as infinite series like this. I trust that you're able to see what's happening here because you see to actually have a fixed ratio to use as a multiplicative factor to multiply to the current term to the next term. And the fixed ratio is actually 3 over 4, right? And by the geometric series. So obviously this case is geometric now. And we can directly apply the geometric series. And because this one is less than 1, and we understand that it is actually a convergent geometric series. And by the comparison test, it means the original series is also convergent, right? And let me write down the answer here. So we can look at the answer in the black box that I've written down here. And that's basically the answer to this problem.